What if we could mimic plants and turn sunlight directly into clean, carbon-neutral fuel? That dream just got a major boost. Chemists at the University of Basel have created a molecule that can store 4 charges at once, 2 positive and 2 negative, a crucial step toward artificial photosynthesis. Let's break down what this means, how it works, and why it matters. Here's what scientists achieved. From sunlight to stored chemical energy, the roadmap starts here. First, why photosynthesis matters. In nature, photosynthesis is the engine of life. Plants take sunlight, water, and carbon dioxide and make sugars, storing solar energy in chemical form. When animals and humans eat those sugars, we release the energy and cycle carbon back as CO2. If scientists could replicate this, we could produce carbon-neutral fuels like hydrogen, methanol, or synthetic gasoline. Burn them, and you'd only release the same CO2 that was captured, closing the loop. Clean, storable, transportable. But the challenge is this: how do you capture enough solar energy in a molecule and store it long enough to drive tough reactions like splitting water? Splitting water and reducing CO2 require multiple charges and sustained energy. That's been the bottleneck. Now here's the new approach. Professor Oliver Wenger and doctoral student Mathis Brandlin designed a special molecule with 5 linked parts. On one side, 2 units give up electrons, becoming positively charged. On the other side, 2 units accept electrons, becoming negatively charged. And right in the middle sits a light-absorbing core that kicks off the process. Hit the molecule with light and it generates 1 positive and 1 negative charge. Hit it again, and you end up with 2 positives and 2 negatives stored at the ends. That's 4 charges total. Exactly the kind of energy buildup needed for chemical transformations. The team demonstrated this accumulation in controlled experiments. Next, why this is different from earlier attempts. Earlier work often used extremely powerful lasers to generate these charges, conditions far from sunlight. This new system works with much dimmer light, approaching everyday sunlight intensity. Importantly, the charges don't vanish instantly. They're stable long enough for follow-up reactions. That stability is exactly what you need to drive water splitting or CO2 reduction into fuels. The Basel team used spectroscopic tools to confirm multi-charge formation under weak light. Working near sunlight intensity is a major step toward practical systems. It reduces the gap between lab demonstration and real-world application. Dim light, lasting charges, and a path toward practical solar fuels. That's why it matters. But it's still a piece of a larger puzzle. Not a full system yet. This doesn't mean we have working artificial leaves powering cars tomorrow. Right now, the molecule can store energy, but it's not yet part of a continuous fuel-producing system. Integration, scaling, and coupling to catalysts for water splitting or CO2 reduction are next steps. Still, learning how to accumulate and stabilize multiple charges is a major leap forward. It provides a foundation researchers can build on. Imagine bottling sunlight into liquid fuels: hydrogen for clean vehicles, methanol for industry, or synthetic gasoline with no net carbon. Clean, storable, transportable, solving 2 of renewables' biggest challenges. This discovery brings the vision of sustainable solar fuels closer to reality. As Professor Wenger said, we've identified an important piece of the puzzle. Artificial photosynthesis won't happen overnight, but steps like this matter. Tell us your thoughts in the comments, and like and subscribe for more science explained clearly.